Welcome to Chapter 4, Part 1. In this chapter, we are going to start talking about alkanes. So, it's sort of like our first functional group. It's organic compounds that don't have a functional group. And there's a lot of topics to cover in alkanes, but let's just start off with some basic vocabulary. All right, alkanes are hydrocarbons, meaning they are composed of hydrogen and carbon. The most basic way that you can combine hydrogen and carbon atoms is with single bonds. So they are hydrocarbons with only single bonds. Hydrocarbons with only single bonds, right? Because if you have multiple bonds, that's when you start to get into alkenes, alkynes, aromatics, right? And those are going to be other functional groups. So when we use terms like saturated versus unsaturated, we're talking about how many bonds to hydrogen are possible. So for instance, the alkane, ethane, has 2 carbons and 6 hydrogens. And we call that saturated. There's as much hydrogen as possible. They are going to follow if they are open chain alkanes, so no rings. They will follow a CnH2n plus 2 formula. That would be as many hydrogens as are possible. So that would be saturated. Anytime you remove possible bonding electrons to hydrogen, you get unsaturation. So what can cause unsaturation would be double bonds, triple bonds, and rings. So if we look at ethylene here, still has just 2 carbons, but notice less hydrogen. We had 6 hydrogen when it's saturated and less hydrogen when it's unsaturated, even less for the triple bond, right? Now, benzene isn't C2, but if you had 6 hydrogen to be saturated, 6 carbon to be saturated, you would need 14 hydrogens. But benzene only has 6. It's unsaturated because of those double bonds and the ring. Now, when we get into each new functional group, and of course, again, we're starting with alkanes, we're going to talk about naming. Now, you did some naming in general chemistry, and you may have even done a little bit of organic naming, but we're going to see naming or nomenclature throughout the year, right? So every time we learn about a new functional group, we are going to talk about nomenclature. And it's really important because there are millions of organic compounds, and many of them will have common names, right? You know that water has the common name water, and then the IUPAC name, dihydrogen monoxide. And some common names are really important to know. Like water is ubiquitous. It is important that you know that word. And there will be common names that you have to learn. And I'll tell you those as we go along. But they're arbitrary. Look at this collection here. Formic acid is named for ants because it is the chemical that is found in, when you get an ant bite, it's the chemical or one of the chemicals that causes the irritation. Urea is named because this is a compound that was isolated from urine, right? So a lot of times the name does give you information about the compound, but it's about where it's from, not its structure. It's not even always going to make that much sense. Morphine is named after the Greek god of dreams, Morpheus. So still a connection, but again, nothing to do with the structure. And then you get to barbituric acid. Bayer named this one after a woman named Barbara, right? It has nothing to do with the structure, where it's found, what it does. It's just random. Some nice woman named Barbara. And so common names can be really important to know, but we'd all just take nomenclature for years to learn all the different names. And so we wind up with talking more about the IUPAC system. So that is the International Union of Pure and Applied Chemistry. And this is a collection of scientists that write rules for us. And something that's really nice about the IUPAC system is regardless of what language you speak, we can communicate about compounds globally this way, but also the name tells us the structure. And if we make a new compound, we know how to name it. Now, we can give it a common name after our favorite woman named Barbara, but the rest of the scientific community doesn't have to rely on that knowledge. So we are going to be talking in terms of the parent. That is often the longest carbon chain. Now, with dealing with alkanes, it's always the longest carbon chain. As we add functional groups, we'll address how the rules change. The parts of the compound that hang off of the parent, otherwise known as the substituents, and then the location of substituents. You'll hear me use the word locant quite a bit. That is going to be the location of where the substituent is attached to the parent. Now, I'm going to come back to this for a second. In every chapter where we learn new nomenclature rules, we will come back to the same basic rules. So it is super important that you learn this now. We will be building off of this naming in chapters 7, 8, 9, 12, and 13, and then several chapters in organic too. If you don't get these rules down now, it will just bother you for the rest of your time in organic. All right, so when naming, first, identify the parent, right? So it is important that you recognize that we are looking for the longest continuous chain, right? Longest consecutive or continuous chain of carbons. This does not necessarily mean it will go from left to right. That is our instinct sometimes. Sometimes it is trickier than that, right? And you may not stumble on, or you may not choose the correct path right off the bat. You may have to troubleshoot, right? If I go through and I go, okay, 1, 2, 3, 4, 5, 6. Okay, well, this compound looks like there's probably a chain with more than 6. So maybe let me start here. 1, 2, 3, 4, 5, 4, 5, 6, 7, 8. Okay, that's a good possibility. But I think I see somewhere where I could get even more. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, I can go around a few other ways and double check, but 9 is the longest continuous chain. All right, so my parent is going to have 9 carbon atoms for this compound. There are going to be 1, 2, 3, 4 substituents, right? Other carbon chains that are hanging off the parent. But first, let's talk about naming the parent. All right, so name the parent. You are going to have to memorize the first 10. And let's see if there is, oh, here it is. Okay, so we identified the parent. We're going to come back to this slide. To name it, it's going to be based on the number of carbons in that continuous chain. So you want to learn these first 10. Now, you can learn more than that. For instance, the next slide tells you some more of the possibilities, but you are only responsible for the first 10. Okay? So they all are going to be alkane, and you're just going to be replacing that prefix. You have methane, that's 1 carbon, and that's going to be CH4, right? They're all going to follow at this point the CnH2n plus 2. That's if there are no substituents. You have methane, you have ethane, propane has 3, and butane has 4, H10. I'm not going to do the rest because I won't have room to fit them in there. But we just go up from there. Now, once you get past 4, those Greek prefixes that you may be familiar with already come in. So you have penta for 5, hex for 6, hept and heptane for 7, oct for 8, non or non for nonane for 9. So we're going to go back and name that first parent we looked at. And then deca for decane for 10 carbons. So again, you need to memorize the first 10. This is going to be necessary for all the naming you're going to have to do. We are going to be building on and altering these 10 prefixes for the whole year. So if we go back and look, right, the parent here is nonane. And that is going to be the base of the name. That's going to be the end of the name when we come back and complete the name here. Now, sometimes you're going to have an example like you see on slide 6 here. There may be multiple ways that you could highlight through that parent where you get the same longest length. In both of these cases, we wind up with 1, 2, 3, 4, 5, 6, 7. We wind up with heptane. So how can we know which is the correct one? You want to pick the one with the most substituents. So on the left, when we highlight or in red here, go through and we find our parent that has 7 carbons with 3 substituents, that is preferable to the one on the left where you only have 2 substituents. It gives you the most, the least complex substituents and allows us not to have confusion in our naming. So you want to choose the longest continuous chain with the most substituents if there is a tie. Now, if you were to draw a path and you got 7 in one way and 7 in another way, and they say they both had 3 substituents, well, then ultimately it wouldn't matter. Both will come out with the same name. It's just if you have 2 different paths and they are indeed different, like we see here with 3 versus 2 substituents. So both of these would be heptane, but this would be the proper way to do the rest of the name. We're going to learn our 10 here. It's nice to know that there are others. You've got the 11, 12, 13, 14, 15, then 20, 30, 40, 50, and 100. And of course, all of the gaps in the middle are filled in. You could certainly look these up if you needed them. You will not be tested over them. All right, now selecting the parent seems simple enough, but we're also going to throw in a little wrench here with cyclic structures. We're also going to be dealing with cycloalkanes, right? And it's the same idea. You're just going to put cyclo in front of it. So we're really still just switching out that little prefix, that ALK prefix. 3 carbons is cyclopropane. 4 is cyclobutane, and 5 is cyclopentane. If we had 10, it would be cyclodecane, right? It's just if it's a ring. Now, the tricky part can be if you have, let's get a new whiteboard over here. If you have a straight chain and a ring. So I want to show you a couple of examples here. Let's say we have a straight chain and then we have, let's say we have a 5-membered ring there. Or perhaps we have a little short chain, and then a 6-membered ring. Well, how are we going to name the parent? Something that you may have learned if you've done some organic nomenclature before is put your pen down, and from start to finish, you need to be able to go through the parent without picking your pen up. And when it's all open chains, that's not a bad way to do it, but it doesn't really help when you have a ring, because you can absolutely start on one end of the ring and then go into the long chain. Don't do that. The parent will be an open chain or a ring. Never both, right? So when we are looking for the never both. When we are looking for that parent, I need to go through and see, okay, the longest continuous straight chain is 1, 2, 3, 4, 5, 6. The longest, or the ring is 1, 2, 3, 4, 5. So the longest chain is the 6. So for this guy up atop, the parent is hexane. However, when I look at the next example, right, the open chain is 1, 2, 3, 4. The ring is 1, 2, 3, 4, 5, 6. All right, 6 is bigger than 4. So the parent here is cyclohexane. Right? Rings can be substituents or they can be the parent. You just cannot have your parent chain have an open piece and a ring. Those are going to be separate. All right. So if we're practicing looking for the parent in these three, we're going to just go for that longest continuous chain, right? 1, 2, 3, 4, 5, 6. So that one's going to be hexane. Here we have to do a little bit of maybe trial and error. Let's say I go 1, 2, 3, 4, 5, 6, 7 with 2 substituents. Okay, what about if I go across 1, 2, 3, 4, 5, 6, 7, but with 3 substituents? So it's heptane either way. I don't know why I wrote it out here instead of just put 7. But this would be the correct parent because it has more substituents than that first way I tried. And then lastly, well, the open chains, there's just one little carbon under each of those dots. But the ring is 1, 2, 3, 4, 5, 6, 7. Sorry, just double checking. So the parent here would be cycloheptane. All right, so you want to make sure that you find the correct parent. After that, we go back and we name the substituents, right? So number 2, substituents. Substituents. And you're going to name them as alkyl substituents. Notice now, instead of an A-N-E, that is the suffix for the parent name. For the substituents, you get a YL suffix. But all of the prefixes are going to be the same. So 1 carbon is methyl, ethyl for 2, 3 is propyl, butyl for 4, and then you get into your Greek, pentyl, hexyl, heptyl, octyl. 9 would be nonyl, 10 would be decyl. You count how many carbons are in the substituent. Now, a carbon cannot be both in the parent and the substituent, right? Notice here how they highlight. The parent is in the yellow box. The substituents are in the green box. There's no overlap. So if we were naming these, it would be ethyl for 2 carbons, methyl for 1, propyl for that 3 carbon one. You can also have cyclic structure, so it could also be cycloalkyl, right? For that one we saw on the previous slide, we had a hexane with a 5-membered ring. right? So the parent would be hexane, but then the substituent here would be cyclopentyl, right? Because it's 5 carbons, but it's a ring. So we're still going to change out that A and E for YL. Right? And just repeating what we said here. And then you put it together, right? So I guess before you put it together, we have to number, right? Get a location. We want locants for our substituents. So for instance, the one that I already have drawn here, I'm going to want to number the parent. And I can number from left or right, but there is a correct way to do it. You want to number in the way that is going to put your substituents in the lowest number position possible. So in this case, I have to number from the right so that that ring is on carbon 3 instead of carbon 4. And then 5, what am I doing? Lost my marbles. 4 is arrange. So a couple of notes here. There is some grammar. You put your number and then a dash and then your alkyl substituent and then your alkane parent. All right. You also arrange them alphabetically if you happen to have more than one substituent. All right. So in this one we have right here, this would be 3-cyclopentyl hexane. All right, if we look at the examples that they have on the slide, the parent is the 6-membered ring, so you get the cyclohexane. And then a 1, 2, 3 carbon substituent is propyl. Now you might be thinking, why is there no number here? Well, when it's a ring, if there's only one substituent, this has to be on carbon 1. And an organic chemist loves to leave out the number 1 if possible. It would be fine to put 1 propyl cyclohexane, but you don't have to because it's a ring. That is never okay if you have a straight chain, right? Unless it's ethane, because then there's only 2 options there. But most of the time you are going to see that number, so feel free to use the number. So in this case, we have a 3-membered ring and a 4-carbon chain. So the 4-carbon chain is the parent. It's butane. The cyclopropyl ring is on the first carbon. Now, in this case, we're numbering left to right. But again, that's only so the cyclopropyl group is on carbon 1 and not carbon 4. Sometimes we will have complex substituents, and I'm going to take that in the next video. So I want to skip that for just a minute. So we're going to run past a couple slides. We'll address that in the next video. I want to make sure that we understand the numbering here. All right. When it comes to numbering, so for instance, methylpentane. There are 2 different methylpentanes. There is 2-methylpentane and 3-methylpentane. There is no 4-methylpentane because, for instance, if I drew what you're thinking of, that is just this compound flipped over. These 2 are the same thing, so they can't have different names. They are both 2-methylpentane. Right? Because of 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. Right? So you want a number to give the lowest numbering possible. There's only 3 is just in the middle. There is no 1-methylpentane, right? If we did this, well, that's just hexane. We just drew it a little different. All right? You cannot have a 1-methylpentane here or a 4-methylpentane. Certainly not a 5-methylpentane. So you can see this is just another example using a methylheptane. you can have this 2-methylheptane, but not 6, because you want to give the lowest number possible. Guideline number 2, you are going to have multiple substituents, so I want to make sure we get through this numbering. If you have multiple substituents, sorry, I'm going to just sing to you. Oh, I'm really sorry for that while I'm writing this out. Okay. Every single one needs a number. Even if there's multiple substituents on the same carbon, they all need a number. Also, if you have multiple of the same substituent, so multiple of the same substituent, you are not going to write it down multiple times. You are going to use Greek prefixes. Prefix. So your di, your tri, tetra, tetra, penta, hexa, hepta, might as well just go all the way with it, octa, nona, and deca. All right, so if we're naming this guy here on the slide, the longest continuous chain is 7. 1, 2, 3, 4, 5, 6, 7. And you want the lowest locant possible for the first one. You want to compare the first place it's different, right? It's not like we're not adding up the locants. 2 is smaller than 3, so 2 wins. It doesn't matter that there's 2 5s. 2 is smaller than 3, so it wins. It's the first one where it's different, okay? So if we're going to name this, and I'm just going to write it over here because I've got room, I have 2, 5, 5. Numbers are separated by commas. Numbers and letters are separated by dashes. So 2, 5, 5, and I have 3 methyl groups, right? I've got 1 carbon, 1 carbon, 1 carbon. 2, 5, 5, trimethyl, and then I can put my parent, heptane. All right, this is the proper way to do it. I found the parent, I named the substituents. I numbered it. I wrote it down using the proper grammar with the commas and the dash and the Greek prefixes. I should not be writing methyl multiple times. If, just looking at this example here on the next slide, you number left to right, right to left, see what the difference is. Whether I number from the left or the right, I get 2. I get a methyl group at 2. But the next one is the deal breaker, right, or the tiebreaker. 3 is smaller than 5, so we go with the one on the left. We would have a 2, 3, 6, trimethyl again, heptane. So you want the lowest numbers possible, but you're going from the lowest one up until you find something that's different. And then the one that's different breaks the tie. If you have multiple different substituents, you have to write them down alphabetically. And I want to do an example before we do the one on the slide here. So for instance, let's say we have, we'll talk about bromine and chlorine here in just a minute. Let's say we have something like this. All right, we've got a parent that is 1, 2, 3, 4, 5, 6, 7, 8. So we have an octane. And we know we need to number it from the left so that we get a 3, 5 substitution pattern as opposed to 1, 2, 3, 4, 4, 6. All right, so we figured out the parent and which way to number it. We have a methyl group and we have an ethyl group. Well, you need to write those down alphabetically. You number them based on the rules we've talked about for numbering, but you write that name down alphabetically. So even though ethyl is on 5, we are going to write it down first. This is a 5-ethyl, 3-methyl octane. All right, so you want to give the lowest numbers possible, and then you want to write it down alphabetically. Now, they're throwing in some halogens here, but they haven't told you about halogens. So halogens are always going to be halo substituents. So you're going to have chloro, fluoro, bromo, and what am I missing? Oh, iodo. So you're going to add those to things you need to know for naming substituents. They're always substituents. They're never the parent. And so when we look at this over here, I've got pentane, right? And no matter which way I number, left to right, I have something at 1 and something at 5. So if everything else is the same, the final tiebreaker is the alphabet. In this case, you would put the bromo first because B comes before C. So this would be 1 bromo, 5 chloro, pentane. Now, again, that only matters if everything else is equal. If you have this scenario, right, your parent is pentane. You have to number it from the left because 2, 3 is better than 3, 4, right? The number is more important than the alphabet. So even though bromine comes before chlorine in the alphabet, the numbering is the most important. However, when I write it down, I'm still going to write the bromo down first. Right? So that one would be 3 bromo, 2 chloro, pentane. All right. We are going to do some more practice in the next video. That's kind of what's coming up here. And I'm going to stop here and we will cover complex substituents and get some practice down and other things you might encounter along the way in part 2.